Okay, well, we've seen the definition of eigenvalues, so one example on how to find them. Now we're just going to go through and do some examples. So for the first example, suppose I have the derivative of a vector is equal to matrix A, 4, 18, minus 3, minus 11, x. And we're going to try to find the eigenvectors and eigenvalues. Notice this implies we have a 2 by 2 system, so our x is some x of t and y of t. It's the only thing that makes sense for that. And I'm going to need to get two eigenvectors in order to see if I get a solution to this. So I'm just going to go through, find the eigenvalues. So I'm going to take the determinant. So before I did a minus lambda I, but notice I is all zeros but has ones on the diagonals. So all this does is says take lambda, subtract lambda from every diagonal entry. So my two diagonal entries are the 4 and the minus 11. So I subtract the lambda from there to get this term, and then I'm going to leave everything else alone, and I want that determinant to be 0. This is a 2 by 2 system, so I can just use the definition. So multiply the two diagonal terms, and subtract the product of the two off-diagonal terms. So let's FOIL this out. I can get minus 44 minus 4 lambda. I'm going to have plus 11 lambda squared. So that's from expanding all that out. Then I'm going to have minus a minus 3 plus 3 times 18. So let's see, this is going to be minus 44, minus 4 lambda plus 11 lambda. It's going to be plus 7 lambda plus lambda squared, and then 3 times 18 is going to be 54. So this is going to be lambda squared plus 7 lambda. 54 minus 44 is plus 10. And again, if you immediately see how to factor this, do it. Otherwise, just go to the quadratic equation. But I can see that this is lambda plus 5 times lambda plus 2. Is that right? 5 lambda plus 2 lambda is 7 lambda. All right, so that means lambda is either minus 5 or minus 2. So I've got two eigenvalues, and that's a good feeling. I'm going to get an eigenvector for each. So that means I'm going to have a solution to the DE. So now I'm going to determine V1 and V2. So lambda 1 is going to be my minus 5. Lambda 2 is going to be my minus 2. So first for lambda 1. So if I come back into this equation here, so this is my a minus lambda I. I'm going to have 4 minus a minus 5. 18 minus 3, this is going to be minus 11 minus 5 times my V1, which is xy, is going to be 0, 0. Right, this is coming from this term right here, which came from our a minus lambda I v is equal to 0. So I'm just plugging in lambda equals minus 5. So let's clean that up. 4 minus a minus 5 is 9. 18 minus 3. Minus 11 minus a minus 5 is a minus 11 plus 5. And that is going to be 16. Is that right? No, something's wrong. It should be minus, it's 6. Sorry. No, it should be minus 6. Yeah, okay. So now I put this in my augmented matrix. By the way, at this point, this is always going to be 0. This is always going to be 0, so I don't really need that. But let's see what I'm going to take 1/9 row 1. So that can be a 1, 2. And here I'm going to take minus a 1/3 row 1. That'll give me a 1, 2, 0. So I can immediately see that if I take row 2 minus row 1, I'll get 1, 2, 0 for the top row, then 0, 0, 0. So I get x plus 2y is 0. So x is minus 2y. So for my v1 is xy. X is minus 2y. So if I factor out a y, I get minus 2, 1. So let me rewrite that. So here I had lambda 1 was minus 5, and v1 is any number, right? Because y could be any number times minus 2, 1. And if you don't have that in your answer, if you don't have infinite solutions, you did something very wrong. All right, so what do we have? At this point, we have the differential equation. We have lambda 1 is minus 5, and v1, so my eigenvalue of minus 5 has an associated eigenvector, v1, of any number times minus 2, 1. Now for lambda 2 is minus 2. Right, so we were looking at a minus lambda I. And that's going to be 4 minus a minus 2. And I leave the off-diagonal entries alone. Then minus 11 minus a minus 2. So 4 minus a minus 2 is 6. 11 plus 2 is minus 9. So for my augmented matrix, I get 6, 18, then minus 3, minus 9 with zeros on the right-hand side. Let me take 1/6 row 1. I'll get 1, 3, 0. And take minus 1/3 row 2. I'll get 1, 3, 0. So this says that x, let me take one more step, just to be pedantic. If I take row 2 minus row 1, and leave the top row alone, I get 0, 0, 0. Again, I need to have a row of all zeros, at least one. And this says x plus 3y is 0, so x equals minus 3. So my v2 is xy, but x is, oops, this is minus 3y. It's minus 3y, y is y. So if I bring the y out, I get minus 3, 1. So that just said that when lambda 2 is minus 2, v2 is any number, that's what's going on here, times the vector minus 3, 1. So that means the solution to my differential equation is going to be any number, we'll call it c1, times e to the lambda 1t, so that's minus 5t, and that was minus 2, 1. Then I'm going to have any number times e to the, for lambda 2, minus 2t, I have minus 3, 1. Okay, note, this is exponential decay. This is exponential decay, but minus 2 is bigger than minus 5, so my dominant term is e to the minus 2t. So the solution is going to decay like e to the minus 2t. All right, let's do another example. So let's suppose we have derivative of x is equal to minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2, x. So this says our x of t has 3 entries. So it's x of t, y of t, and z of t. And I'm going to need to find eigenvectors and eigenvalues here. I'm going to need 3 eigenvectors. So I'm going to hope they exist. So the first thing I'm going to do is get my eigenvalues. And let's see, so I'm going to take the determinant. So I'm going to take minus 2. I'm going to subtract lambda from each of the diagonal entries. So anything off the diagonal I leave alone. Anything on the diagonal I subtract lambda. I'm going to take that determinant and set it equal to 0. It's not going to matter where I expand, so I'm just going to go across first row. It's going to give me plus, minus, plus. So it's going to be minus 2 minus lambda. And if I remove the first row, first column, I'm left with minus 2 minus lambda 1 for the first row, then 1 minus 2 minus lambda for the second row. Now for this term, so it's plus minus 1. This is going to be, so I move the first row, second column, I'm left with 1, 1, then 1 minus 2 minus lambda, and finally plus 1. I'm going to have the determinant remove the first row, last column, so I'm left with 1, 1 minus 2 minus lambda 1. And I just, at this point, I've got 2 by 2, so I can just grind it out. This becomes minus 2 minus lambda times minus 2 minus lambda, so that's squared, minus 1 times 1. Now I'm going to have 1 times minus 2 minus lambda minus 1. Then here this is going to be plus 1. I'm going to have 1 times 1 minus a minus 2 minus lambda times 1. Multiplying everything through, I get minus 2 minus lambda cubed minus a minus 2 minus lambda. And here I'm going to have minus a minus 2 minus lambda. Here I'm going to have plus 1 minus a minus 2 minus lambda. All right. So this gives me minus 2 minus lambda cubed. I'm going to have minus 3 times minus 2 minus lambda plus 1. All right, so I'm going to have to expand all this out and cube it. I'm just going to, for the interest of time, you don't want to see me expand everything out. I'm going to just tell you what I got. What I did, I got minus lambda cubed minus 6 lambda squared minus 9 lambda. Okay. And notice I can factor out a lambda. So I get minus lambda squared minus 6 lambda minus 9. So I can factor out a negative 1. So I get lambda squared plus 6 lambda plus 9. This is going to give me minus lambda, and this is just going to be lambda plus 3 squared. So I'm a little bit worried because I only have 2 eigenvalues, 0, we'll call that lambda 1, and lambda 2 is minus 3. I may only have 2 eigenvectors. If that's the case, that's going to be a big problem. So let's just go through and see what we get. So now the eigenvectors, and again, our system was the derivative is equal to minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2x. I had lambda 1 is 0, and lambda 2 is minus 3. This was a double root, so that's going to may get weird. Let me do the single root first with the hope that that is not so bad. So let's see, if lambda 1 is 0, I'm going to subtract 0 from each diagonal. So I'm going to get that, which means for my augmented matrix, I want to put this in reduced row echelon form. All right, you've seen me do this. You should be able to do this on your own at this point. You don't need to watch me do this, but you should be able to work with this and get this down to 1, 0, minus 1. 0, 1, minus 1, and 0, 0, 0, 0. If you do not get a row of all zeros here at the end, something bad happened. So what does this say? This says that x minus z is 0. This says that y minus z is 0, which implies that x is z and y is z. So for v1, my solution looks like x, y, z, but x is equal to z, y is equal to z, and z is z. So I get z times 1, 1, 1. So this is any number times 1, 1, 1. For lambda 2 equals minus 3, so now I'm going to subtract a negative 3 from each diagonal entry. So that's going to be minus 2 plus 3 is 1. I leave everything else alone. Minus 2 plus 3 is 1. And then for the bottom row, I'm going to get 1, 1. Minus 2 plus 3 is 1. So for my augmented matrix, I get this. Now when I put this in reduced echelon form, again, I would expect you to go through and do all this. I'm not going to do it just because you don't need to watch me do it. But you should be able to see that if I just take row 2 minus row 1 and then do row 3 minus row 1, I'm going to get all zeros. So I get this. You should be able to go through and do all this on your own. The only reason I'm skipping it is just because you don't need to watch me do it. So this says that x plus y plus z is 0. So this says that x is minus y minus z. All right. So my solution then for v2 is x, y, z. And we just said that x equals minus y minus z. So I replace that. Notice I have two unknowns. X or y and z could be anything. So if I separate these, so anything with a y is in one, anything with a z is in the other. So this is y times minus 1, 1, 0. Plus z times minus 1, 0, 1. So notice now I've got two options here. So there's really two eigenvectors. This would be v2 and this would be v3. So my solution then is going to be anything times e to the lambda 1. So lambda 1 was 0, t, and that eigenvector was 1, 1, 1. And now I'm going to have e to the lambda 2, t, that was minus 3t, all times c2 minus 1, 1, 0, plus c3 minus 1, 0, 1. All right, because I could have any number for y, any number for z, and this is now my solution to the differential equation. Note, this decays and goes to 0, and this is going to stay constant. So the dominant term is now this thing, never goes away, it just stays constant, and this thing decays to 0. So basically, in the long run, I expect my solution to just get close to that.